So, yeah, good afternoon. Are you enjoying the conference so far? Yes, all right, it's getting towards the end of the second day. You're probably a bit tired. I'm kind of getting that energy. But thank you so much for choosing to attend this session. I really, really mean it. This is a really tough slot up against Dylan Beattie and David Whitney. I would be at their talks, actually, if I was not here. They're both excellent speakers, and I'm very lucky to be able to call them my friends. I mean, they don't refer to me as their friend, but a girl can dream. And also, yeah, as I said, if you are here for Erwin's talk about infrastructure as code, you are in the right room at the right time, but Erwin is not. And this talk is about plane crashes, not the train wreck that is YAML. So anyway, thanks for being here. And believe me when I say this comes from a pure, genuine place of self-interest. I can assure you that you've made a good choice to attend this session. So, quick intro, my name's Adele Carpenter. I'm a software engineer at Trifork Amsterdam. Most of my day I spend building and maintaining Kotlin and Java applications for the educational sector, although more and more lately you'll find me trying not to cause too much damage with React in the front end. So, as the title of this talk suggests, this is part 2 of a topic I have spoken about before. So, has anyone seen part 1 of this talk either in person or online? Yeah, a couple of hands. Okay, so that's fine. Welcome back, people that have seen this talk before, or this topic before. And if you haven't seen anything, it's fine. Part 1 and 2 are completely standalone, so you will not be playing catch-up at all. So while I am really proud of part 1 of this talk, perhaps I was a little bit too ruthless with the detail that I left out in order to tell a nice story in a digestible way. So I'm going to revisit that choice and provide a little bit more history and context to civil aviation, the study of aviation disasters, and of course what we can glean from that as software professionals. So first up, we're going to have a little bit of an overview of the first 50 or so years of aviation, and this always boggles my mind that 120 years ago we were simple ground dwellers, and now, well, we are simple ground dwellers with flying machines. And I don't want to spend too long on this, so buckle up because I'm going to keep the pace really, really high. So this is a bare-bone timeline from 1903 to 1950 or so, and I'm just going to run you through it really quickly. So aviation as we know it started with the Wright brothers in 1903 with the first man-controlled flight. Just over 10 years later, when World War I rolled around, developments accelerated to match the new technology with the requirements of the battlefield. And between World War I and II, there was some space for a bit of fun, and we saw the first airlines, daily passenger routes, air shows, and transoceanic flights. But when the fun stopped again with World War II, developments in aviation kept accelerating. Now, most of the developments were around air-based weaponry, of course, but we did see more general improvements, such as improvements in manufacturing and the development of the jet engine. And after the war, humanity had the space again to focus on commercial aviation. And we saw air traffic grow by about 20% per year. So by the time that we get to this point in the late 1940s, we have a paradigm-shifting technology whose early development was catalysed by not one, but 2 world wars. And this was followed then by a period of rapid adoption and growth in the civilian sector. So what do you think is going to happen at this point? Disaster, of course. So here's a summary of the causal factors of plane crashes from 1950 until 2019. I got this table from a website creatively titled planecrashinfo.com. And I debated whether or not I should recreate this table for you in a more aesthetic and less grainy way, but actually I kind of love it. Like, I know it looks like it hasn't been updated since 1996, but this website is actively administered, and the latest crash in the database is from April, just gone, so a couple of weeks ago. And aviation geeks, they're not really that different from dev geeks. We, the dev geeks, have the slicker online tools, but the level of detail, care, and precision is essentially the same on both sides. So the Venn diagram of both communities is almost a circle. And just a quick note before we do move into the numbers. Now, be aware this covers fatal crashes only, where at least 2 people have died. It also only looks at civil aviation, so military is not included at all in these figures. So now that you've had a little bit of time to digest it, even with me up here making terrible jokes, I do hope that one thing has leapt out to you, and which is that over the decades, the most common cause of fatal air crashes is pilot error. And you may have also noted that the breakdown by these 4 broad categories is relatively consistent, although we can see that mechanical causes have reduced since the 1950s and 60s. Now, worryingly, if we look a little bit closer, we might want to infer a jump in the number of crashes caused by pilot error in the 2010s. Now, later we'll discuss a case study that hints at why, but for now I want to take a look at the actual numbers, because if we look at the actual numbers rather than the percentages, it tells us a different, more hopeful story. And again, with the beautiful formatting courtesy of the source website. So here we see a peak of the crashes in 1970 at 230, with pretty remarkable attenuation after that, dropping every decade until the 2010s, until we are left with 49 fatal crashes and 28 of them due to pilot error. Now, please bear with me here another 30 seconds as we paint the final bit of the picture here. So here we have the global fatalities per million passengers, consistently dropping for decades. And we're now hovering at around 1 death per 10 million passengers. Now, climate issues aside, aviation is an incredibly safe mode of travel, and it had only trended towards safer. And this is an engineering success story that I think we can learn a lot from. Because one thing that I really appreciate about the aviation industry is the deep understanding that there is rarely one cause for something. If you read the final air crash investigation report, and believe me, I have read more of those than I care to remember, you will find typically that there's a list of causal factors and a list of contributing factors for a crash. Disaster isn't something that just spontaneously happens. Often many systems, people, process, mechanical, have had to break down for disaster to occur. So with that in mind, there was one change in the late 1970s, early 80s, that did drastically reduce the number of crashes attributable to pilot error. And that was the expedited introduction of crew resource management after the crash of United Airways Flight 173 in 1978. Now, I cover that crash in a bit more detail in part 1 of this talk, and you can check it out on YouTube if you are interested. But in short, while working on resolving an issue with the landing gear, the captain was unaware that the plane was running out of fuel. And a causal factor of this crash was a breakdown of communication in the cockpit. The captain didn't ask, nor did the co-pilot assertively communicate the severity of the fuel situation. And in the end, they did run out of fuel, and 10 people lost their lives. And crew resource management teaches airline crew how to make effective use of the resources available to them to ensure the safety and efficiency of the flight. Now, this includes equipment, procedures, and people, both inside and outside of the cockpit. Now, originally, this was just introduced for pilots, but now it's an important part of training for cabin crew as well as ground crew. And this has really been a big driver in the reduction of crashes related to pilot error. So in the 2000s, we saw another drop in crashes attributable to pilot error as CRM was expanded into emerging aviation markets. And the 1990s and 2000s also saw wider adoption of fly-by-wire technology and flying automation, accompanied by enhanced protections and warning systems. So if you consider this in the context of continuous improvements to maintenance procedures, training, and regulatory oversight, then this really led to a big period of big leaps in aviation safety. And even crashes due to the weather dropped in this period as airports gained access to better meteorological data and aircraft were fitted with advanced features like wind shear detection systems. Now, if you don't know already, wind shear is the pants-browning experience of a sudden change in wind direction. So you can imagine that you are close to the ground and you get a sudden gust of wind downwards, just how dangerous that could be. And the widespread introduction of airborne wind shear detection alert system was a key recommendation after the crashes of Pan Am Flight 759 in 1982 and Delta Airlines Flight 191 in 1985. So in this respect, these crashes were instrumental in advancing weather-related safety in aviation. And while it certainly is true that technological advancements have been a significant driver of improving aviation safety, it would be remiss of me to gloss over the fact that this has brought with it significant challenges. And I think the discussion and appreciation of these challenges is where the real gnarly insights for software professionals, where they lie. So, fly-by-wire and its related systems has really opened the door to a lot of questions surrounding the pilot's role of flying the aircraft and the limitations of humans when it comes to understanding and interacting with automation. Now, fly-by-wire was first deployed on Earth with the F-16 in 1974. I say on Earth because fly-by-wire was actually deployed on the Apollo missions, but space travel is outside the scope of this talk. If you want to hear about space travel, you should go to the other room to the NASA guy. So for our purposes today, fly-by-wire started with the F-16. So anyway, traditionally fixed wing aircraft are controlled by a control column or a yoke, and this yoke is mechanically connected to the flight control surfaces of the aircraft. So when the pilot pulls the yoke back, this is a direct input on a cable which moves the elevators up, driving the tail down and therefore the nose up. And the key point here is that there is a cable or rod running from the cockpit to the tail and the other flight control surfaces. Now, in fly-by-wire, the flight control computer accepts a pilot input to the controls and manipulates the control surfaces in such a way as to produce the pilot's desired result. So essentially, the flight computer acts like a middleman for the pilot's instructions, a much lighter, smarter, and opinionated middleman than traditional cables and rods. Now, this middleman can and does provide protections to ensure that the aircraft stays within its safe flight parameters. So if the pilot is trying to pitch the nose so far up that the plane starts to lose lift and enter a stall, the computer will be like, nah, I don't reckon. And it'll make just a much smaller adjustment to the flight control surfaces. So in the words of the early F-16 pilots, you don't fly an F-16, it flies you. So moving back to the commercial realm now, in 1988 we saw the launch of the Airbus A320, which was the first airliner with fully digital fly-by-wire controls. It was also a key moment in what has come somewhat diverging philosophies of Airbus and Boeing with respect to automation. So Airbus's stance is that automation should allow the pilot to use the safe flight envelope to its fullest extent. And the flight envelope is basically the safe flight parameters or operating limits, of the aircraft, although this can vary based on weight, speed, and altitude, amongst some other things. So at a certain weight and speed, for example, there is a safe range of altitude. And it's also where the English expression pushing the envelope comes from, to mean pushing the limits of a situation. Now, the flight computers on Airbus aircraft follow a series of laws that each offer various levels of protection. And a protection is basically a nah, I don't reckon response from the flight computer. And these three laws are called normal, alternate, and direct law. In normal law, you have the most protections, and in direct law, you have the least. And I think it's a very telling design decision from Airbus that it's actually not possible for the pilot to decide which law they want to operate under. And this is always determined by the aircraft. And the only way that I could say this is to say that Airbus takes a computer-centric approach. Now, one of my friends is a fellow speaker, not here at this conference, but on the circuit. He's actually an airline pilot himself, and he said there is actually a workaround to change the mode that you're in, but it's not exactly sanctioned, but it can happen. So Boeing, on the other hand, they've traditionally taken a much more pilot-centric approach. And they did, in 1994, introduce the 777, which is fully fly-by-wire, and later the 787 Dreamliner. However, the highest-selling aircraft, the 737, decidedly has mechanical controls. And just a quick nod here to the elephant in the room called Max, because we have seen some deviation from that approach recently with the introduction of the MCAS in the 737 MAX 8. But that's like a little bit of a special case, and it is worthy of its own talk. And you're in luck, because there is a talk about the MAX 8 from a guy called Kyle Kotowik. I saw it in Belgium last year. I highly recommend it. He's been giving that talk for a while, so you can easily find it online. He's actually speaking during the party later, so if karaoke is not your thing, I can highly recommend him as a speaker. So in any case, I'm not in a position to make a claim about which approach is better, a pilot-centric approach or a computer-centric approach, if one is at all. However, I do find the fact that the two largest aircraft manufacturers, despite traditionally putting the same priority on aviation safety, have taken two different approaches to achieving it. Because what are the appropriate roles of human and machine when it comes to machine-assisted decision-making? Because we're facing that question right now with the introduction and rise of AI tooling. So while we're on that topic, did you all catch the Layla's keynote yesterday? Yeah, she did an excellent job of addressing some of those questions, and I loved every single second of that talk. So I hope I can provide here a little bit of a different angle and insight from aviation. So I won't be talking about AI specifically, but hopefully you can see the parallels between what we're seeing with AI today and the issues that aviation has been grappling with for decades already with respect to how humans and machines interact. And I think there is one air crash that sums up these points really, really well, and I'm going to share it with you now in a storytelling format. Now, I do warn you, it's quite heavy, and it's also relatively-ish recent. It is the heaviest part of the talk, but it does set us up for a nice discussion afterwards. So just to break the suspense a little bit, while I get some water, the flight is Air France 447, which crashed into the Atlantic Ocean on June 1st, 2009, as it was returning to Paris from Rio de Janeiro. All right, and it's just a quick little warning here to prepare your eyes a bit, because we're going to enter dark mode. All right? So it's June 1st, 2009. Air France first officers Daniel Robert and Pierre-Cedric Bonin are in the cockpit of the Airbus A330 over the mid-Atlantic Ocean. Now, Bonin, the less experienced of the two pilots, is the pilot flying in the right-hand seat, and Robert is the pilot not flying, or the pilot monitoring, in the right-hand seat, the captain's seat. Well, wait, where's the captain? You might be wondering. Now, this is a 14-hour flight from Rio to Paris, and the allowed duty time of 10 hours for these pilots will be exceeded. So in order to complete the flight safely and manage fatigue of the crew, the three pilots rotate so that they can each get some rest and remain alert while they are in the cockpit. So Captain Dubois has just stepped out for his rest, and there's nothing out of the ordinary here. But Bonin is feeling a little uneasy. He's flying through the intertropical convergence zone in June, and as is common at this time of the year, he's experiencing some light turbulence as they fly through a layer of cloud. He had discussed the weather with the captain just before Dubois took his rest. He'd proposed a couple of small adjustments that could make to the flight path to potentially avoid the worst of it. But Captain Dubois is not particularly concerned, and the proposed changes also carry some risk. So Bonin and Robert notice some ice crystals in the cloud layer, and they turn on the anti-icing system. Less than 3 minutes later, an alarm sounds. The autopilot has disconnected. "I have the controls," says Bonin. Robert confirms. And the plane rolls from side to side a little as Bonin settles into flying the plane manually. He pitches the nose up. We haven't got a good indication of speed, he says. The autopilot has disengaged because the flight computer can't make sense of the conflicting airspeed data it is getting. And the data is bad because the sensors are clogged with ice crystals. Alternate law, protection's low, says Robert. In alternate law, there is still some support from the flight computer, but critically, there is no anti-stall protection. And not long after Bonin takes the controls, the stall warning sounds. The stall warning is designed to be as intrusive as possible. So you've got to think of the loudest crickets that you've ever heard and multiply it by 10, and that's on top of the continuous C chord master as well as multiple visual alerts. Like, this is pure sensory overload these pilots are experiencing. And Robert adds to what must be overwhelming noise in the cockpit. Watch your speed, watch your speed. Okay, I'm going back down, replies Bonin. According to all three, you're going back up, so go back down. Bonin reduces his nose up input and thrust, and the stall warning temporarily stops, although there were still several other warnings demanding their attention. The pilots have control of the aeroplane again, yet confusion remains. Unbeknownst to them, the airspeed sensors are now ice-free and the avionics are functioning normally again, although there is still curious behaviour from some instruments. They still don't have a full grasp of the situation. Robert focuses his attention on summoning the captain. Damn it, where is he? The stall warning starts again. I'm in toga, right? Says Bonin. Toga is short for takeoff and go around, and this setting provides the maximum thrust needed for the plane to take off with the nose pitched up. It is designed to be applied at lower altitude where the air is heavier, and this statement hints that Bonin has, to quote the investigation report directly, built an erroneous representation of the aeroplane's flight model. And the fact that his actions are not resolving the warning deepens his mistrust of what the aeroplane is telling him. And he may be further emboldened by the fact the A330 carries robust anti-stall features. Anti-stall features that are not available to him in the current flight computer state of alternate law. I don't have control of the aeroplane anymore now, exclaims Bonin. Controls to the left, asserts Robert. 8 seconds later, Captain Dubois enters and takes a seat behind Robert and Bonin. What are you doing? What's happening? I don't know what's happening, says Robert. We're losing control of the aeroplane, confirms Bonin. Over the next 2.5 minutes, the three pilots try to understand and resolve the situation. Captain Dubois recognises that they're in a stall, and Robert pushes the nose down to try and gain airflow over the wings. More airflow, more lift. But they cannot regain control of the aeroplane. When they get dangerously close to the sea, Robert reverses inputs by pulling back and says, climb, 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 climb. Chillingly, Bonin responds, but I've been nose up for a while. Captain Dubois pleads, no, don't climb. Give the controls to me, says Robert. Go ahead, you have the controls. We're still in toga, yeah, replies Bonin. Robert spends the next 35 seconds trying to recover the aeroplane, but it's too late. Moments later, Bonin exclaims, we're going to crash, this can't be true. And the cockpit voice recording ends along with 228 lives. So I read the transcript of this flight many times, and it still sends a chill down my spine every time that I read it. For obvious reasons, the real recording hasn't been released, but I can just imagine the investigators like sitting there dumbfounded as they're listening to it. And it's really easy to blame the pilots for this crash, and many people have, including the press and the courts. And to say that they're not at all responsible for the crash would also be incorrect. But as someone who didn't lose a loved one in this disaster, I have the luxury of being able to avoid the blame game and instead focus on what we can learn. And do you see here in the subtitle the implication that the pilots were shirking their responsibilities and sleeping on the job? A sleep mandated by safety requirements. This is classic tabloid journalism. Anyway, I digress a little there. So Air France 447 highlights something that I don't think we think about enough as software professionals, and that is how humans interact with complex systems, particularly those that have a lot of redundancy. And there's a tendency to think that outside of cost considerations, more redundancy is better. And in safety critical systems in particular, you're willing to take on those extra costs in order to have that extra safety or fallback. And even in non-safety critical systems, there is this level of expected redundancy. And the classic examples being backups and having your application running in multiple regions or data centers, or running your database or message broker as a cluster. And indeed, in my team at Trifork, we run our own cluster of 3 nodes of our message broker, RabbitMQ, 3 of course being the magical minimum number for redundancy. And recently we encountered an issue that caught us a bit by surprise and resulted in 8 minutes of downtime of our main application during a busy period. So show of hands if you've used or have used, you're using or have used RabbitMQ in production. Okay, a couple of hands here. So let's see if we can figure out what's going to happen as I tell the story. So just like you would see in the cockpit, we started receiving alerts about an unexpected state. We had a growing number of messages in our production queues, in addition to disks that were getting dangerously full. And the number of messages in the 2 queues was around 600,000 each, which was high but not unexpected during a busy period. However, the rapidly shrinking disk space was concerning and the message throughput was slow. And we decided that a low-risk first course of action would just be to restart one of the affected applications listening on one of the queues. But unfortunately, that didn't resolve the issue. Now, after some back and forth in the team, and with the desk getting ever more full, we decided to take the secondary RabbitMQ server offline and bring it back with extended disk space. And at first, this seemed to go well. We took the node off without a problem, and the application was still limping along, serving requests with fewer nodes. But there was a key part of this redundancy model that we didn't understand. Because these classic queues were very large, still in total over 1 million messages, when we reattached the node to the cluster, the node started to sync itself to the queue, basically stopping time while it copied 1 million messages. And all we could do was wait. Now, during what felt like the longest 8 minutes of my life, no messages could be consumed at all, and as such, our main application was unavailable to our users. So those with the Rabbit experience, did you guess correctly? You did? You knew that would happen? Yeah. And because that happened to you, or because you're the only developer on the planet that reads documentation?
Someone else I know it happened to.
Okay. So this isn't a perfect example, but it shows the perils of interacting with complexity and redundancy when under pressure. Now, probably someone in the team should have known about the sync time on such a big queue, but once set up, like, the queue just kind of works. So back to the Airbus, here is a schematic of the systems involved in providing aerodynamic and inertial parameter data to the pilots of an A330. So ADIRU is short for Air Data Inertial Reference Unit, and you might recall that the first part of the Air France 447 story, the autopilot disconnected due to conflicting airspeed data. Now, the air data part of the ADIRU is most notably responsible for providing the calibrated airspeed and Mach data to the pilots. If you're really smart, you're thinking, wait, isn't Mach speed as well? Well, then you're right. Mach is presented as a fraction of the speed of sound, and calibrated airspeed is presented in knots. Now, I'm oversimplifying a lot here, but above about 28,000 feet, Mach actually becomes the more important measure of airspeed. Now, the inertial part of the ADIRU provides data such as the ground speed and the attitude or pitch, so the number of degrees that the nose is pitched up or down relative to the ground. So you can see here on the left and the right side the physical sensors that provide data to the ADIRUs. And without getting too bogged down in specifics, airspeed data is calculated from static air pressure and total air pressure. And there are 6 static air pressure sensors on the A330. And the total air pressure is measured by something called a pitot probe, which is a small tube that sticks out the side of the fuselage. And the A330 has 3 pitot probes circled here in green. And you can see here that the data from pitot 1 feeds the captain's flight display, pitot 2 feeds the co-pilot's display, and pitot 3 feeds the standby flight display. And you can see something here called ISIS, which is an unfortunate name, I know, especially on an aeroplane, which is the Integrated Standby Instrument System. Now, this is designed to serve as a backup in case of a failure of one of the standard flight displays. So you can forget turtles here, like this is redundancies all the way down. So we have redundancy of data, given that we have multiple sensors measuring the same thing. We have the static redundancy of the 3 ADARUs, where an error in one system can be outvoted by the other 2 systems. We have redundancy of top of those 3 flight display systems with an external computer system that integrates the information from a variety of sources. And now, if you're feeling overwhelmed, confused, unsure, or simply bored right now, then you already understand the point that I'm trying to make, which is redundant systems do not operate in isolation. And when they work, they're great. When they fail hard, often in unexpected ways. And often what you find at the other end are some humans under immense pressure to not only figure out what is happening, but also to save the day. Now, in the case of Air France 447, the cascade of unfortunate events started with the loss of reliable airspeed information due to the pitot probes icing over in the absence of the captain. The autopilot could not make sense of the conflicting airspeed data it was getting, so it disconnected. Let the humans figure it out. The aeroplane displayed an abundance of alerts and messages to the co-pilots who had not encountered the situation before, not even in the simulator. And to make matters worse, many of those messages were about the consequences of the problem rather than the origin of the problem. And then, unable to make sense of what was being presented to them, the pilots failed to diagnose the situation correctly and apply the appropriate checklist. And under stress, possibly suffering from the startle effect and possibly reacting to the intermittent appearance of the crossbars on his display, Bonin pitched the nose up. And he had little practice flying the plane manually at altitude and was used of the A330's anti-stall protections. But the anti-stall protection was gone once the computer shifted into alternate law. This is a fact that Bonin was expected to recall within seconds. Actually, the FAA, the US Civil Authority, they think that pilots should be able to recall such information within 3 seconds. Now, tragically, the attempts of Robert to push the nose down to gain airspeed over the wings and recover the stall proved futile due to the design of the cockpit and the controls and the fact that it was dark. Robert could not see Bonin's side stick was being pulled back as he was pushing the nose down. And the conflicting inputs of the pilots, one nose up, one nose down, effectively cancelled each other out, which just added more confusion to the situation. So when Bonin finally exclaims, "But I've been nose up for a while," that was when the penny dropped, but it was far too late. And Air France 447 is basically the poster child for automation gone wrong, and the media certainly had a field day with this narrative. But the more interesting and less tabloid-worthy discussion for me is, how do we design more human-centric systems in a digital world? Not just for users, but for ourselves as developers. Because I really dislike this approach of, oh, well, if the unexpected happens, say, I don't know, and hand it back to the users. I mean, maybe you can get away with that with simple systems, but as the system gets more complex, maybe with parts of it written by AI, then you're actually demanding a lot from your users. So at best, your user gets annoyed, but does in fact try again later. And at worst, you have a plane falling out of the sky. And somewhere in the middle, there's me holding my breath for 8 minutes while a new node syncs a queue of 1 million messages while it connects to the cluster. And somewhere next to me, there's you having a mini meltdown because your Slack is blowing up and your exquisite dashboards are disintegrating into an amber and red mess. And in the corner, there's Pete having a great time with his headphones on and his alerts muted because the alerts don't usually mean anything anyway. And in order to start thinking about human-centric design, you've got to understand some simple features of humanity, or depending on who you ask, bugs of humanity. And aviation has certainly encountered most of them. So the first one is that we have a limited working memory. So are you familiar with the concept of cognitive load? Yeah. A lot of nods. So just quickly, cognitive load refers to how much of our working memory is required for a task. So you may have heard that our working memory can hold 5 to 9 chunks of novel information. But the number that shocked me is that only 2 to 4 of those chunks can be worked on or thought about at once. The cool part, though, is that this limitation applies to novel information only, not information that we've already stored in our long-term memory. So for pilots, this highlights even further the importance of relevant training and experience to free up as much working memory as possible for truly novel information. And as developers, what we can do is we can strive to make the way that people interact with our systems as consistent as possible. So consistency over correctness is absolutely not a dead concept. So Copa Airlines Flight 201 highlights the importance of consistency and human-centric design even further. In 1992, a Boeing 737 crashed in Darien Gap, a region of almost impenetrable jungle in Panama. And despite the immense challenges of the terrain, the investigators were able to piece together the flight data recorder and collect the bulk of the wreckage. Now, a key piece of the puzzle is from the captain's vertical gyro. And the gyro is the data source for the attitude indicator shown here, which I think is the instrument most people are readily able to associate with flying. And the one here is similar to the one found on Copa Airlines Flight 201, and it shows the plane in relation to the horizon. And it's very, very difficult to fly without it, especially at night. So given that it's so critical, the smart engineers built some redundancy in. So similar to what we saw with the airspeed data in the A330, there is a gyro on the captain's side that feeds the captain's display, and there's one on the right side to feed the co-pilot's display, and then there's an auxiliary gyro to feed the standby display. So if you identify an issue with the data of one of the gyros, for example, the captain's gyro, then there is a switch where you can set the data source for both displays to be the co-pilot's gyro, like this. And so, similar to what we saw in Air France 447, Flight 201 starts receiving bad data, which causes the autopilot to disconnect. And this time, the faulty data source is from the captain's gyro. So in the dark, the pilots need to manage flying the plane with a broken attitude indicator. And the investigators can only be shocked when as the flight data recorder tells them a horrifying story of the pilots repeatedly reacting to bad data until they eventually roll the plane out of the sky. And the obvious question is, why didn't they just switch the data source? So here's how the switch appeared when it was pulled from the wreckage. So it says both on VG, or vertical gyro 1. So this means that the pilots had identified that they were getting bad data, but then pointed both displays to the bad data source. What on earth were they thinking? So let me show you the same switch as it was installed on the simulator that the pilots were trained on. So, do you see it here? So, putting aside the fact that it's an entirely different switch altogether, in the simulator, left means give the captain the auxiliary data, and in the plane, left means switch the co-pilot to the captain's bad data source. So, This is deadly UX, if you were ever going to see it. The simulator does the exact opposite of what the aircraft does. And it's about the most extreme example of consistency over correctness that you are ever going to get. So moving on now to the second bug of humanity, which is that we have a blind spot for our assumptions. So in 1989, British Midlands Flight 92 crashed while attempting an emergency landing. And the first sign of trouble in the cockpit was a loud pounding noise and a severe vibration. In the cabin, smoke poured in, and some passengers could see sparks coming from the left engine. And whilst the pilots were very, very experienced on the 737, they only had 76 hours combined on this particular version, the 737-400. Now, in previous versions of the 737, the right air conditioning system receives what's called bleed air from the right engine as it supplies air to the cabin, and the left does the same for the cockpit. However, on this newer version, the air from the left and the right is mixed before it re-enters the aircraft. So the captain, relying on his experience, sensed the smoke coming forward from the cabin and assumed that the fault was with the right engine. And based on this shared assumption, he and the co-pilot powered down the engine on the right. Now, unfortunately, as bad luck would have it, at the same moment they did that, the auto throttle disengaged, which reduced the fuel flow to the left engine. So as a result, the fire weakened and the smell of smoke subsided, which seemed to confirm to the pilots that they had made the right decision or taken the right course of action. But when they start the approach for the emergency landing, they increase the thrust and they grow the fire to the extent that it kills the left engine entirely. So at this point, they are travelling far too slowly to restart the engine on the right, and they crash right next to the motorway. So I have a little bit more to say about the Midlands crash, but before I do, I want to introduce the next bug of humanity that we'll be discussing today, which is we do irrational things. So despite heavy protests to the contrary, rational people do irrational things. Yes, even developers, and yes, especially users. And British Midlands was one of two crashes in Britain in the 80s that were pivotal in improving the survival rate of survivable crashes. And no, not because everyone got a lecture on verifying their assumptions before acting, although that would be useful for most people. I'm sure you've already got a colleague in mind who could benefit from that lecture. So of the 126 passengers and crew on board Midlands Flight 92, 79 people survived, with 74 of them suffering injuries. So by examining the injuries and the aircraft, a number of recommendations were made relating to aircraft itself, such as improvement to seat floor and overhead bin design. There were also changes made to the recommended brace position and the restraints of young children. But the survivors of the Midlands crash had already benefited from the 1985 Manchester airport disaster, which had happened only 4 years earlier. Now, in this crash, there was an engine failure during takeoff, which generated a fire. And the takeoff was aborted, and the captain ordered an evacuation. So, of the 137 passengers and crew on the flight, 55 died, mostly from smoke inhalation as they attempted to rush, climb, fight, and squeeze their way to the emergency exits. And so the Manchester airport disaster forced aircraft manufacturers to consider the behaviour of a group of humans facing death, behaviour which in most other contexts would be completely irrational. So these changes included making it easier to find the exit by installing the strip lighting, creating more space for exiting the aircraft by removing a seat at the overwing exits, and by widening the entry to the galley, otherwise known as the place where the terrible coffee is made, installing fire suppression systems, in the cabin, and the introduction of less flammable materials for things like seat cushions and carpets. So only like a few small changes. You can implement it in a weekend, no problem. So for the airlines, the changes included spreading crew of different experience levels throughout the aircraft and a pre-flight safety briefing for the passengers sitting in the exit row. So if you are sitting in the exit row and you're getting the safety briefing, 55 people died for you to get that briefing. So digging down a little bit more now to an individual level, irrational choices are often driven by bias, emotion, and stress. So in the final report of Air France 447, investigators mentioned that the crew acted irrationally in response to the anti-stall warning, probably due to the startle effect. Now, ongoing training is often repetitive and well-known, repetitive and well-known, repetitive and well-known to the crew. So this blunts their ability to truly react in a measured way to the unexpected. But I think the bigger point here is about the role of stress in your users' behavior. So have a think about the stress that your users could be experiencing. For example, noisy environments or a poor internet connection. How can you make it easier for them to interact with your application under those circumstances? And the last bug/feature of humanity that I would like to mention today is simply that we get used to things. Now, as was the case with Pete and his muted alerts, repeat application of a stimulus tend to result in a decreased response. So in psychology, this is called habituation. So if your alerting is too eager, eventually you'll start to ignore the alerts, putting you in the same position as if you had no alerts. And another manifestation of getting used to things is simply going through the motions. So even if something does have a high risk of going wrong, if you do it enough, you can become complacent. So in 1988, Delta Airlines Flight 1141 crashed shortly after takeoff because the flaps weren't deployed. So these things here. And as you can see, the flaps extend out the back of the wing during takeoff and landing. And they extend the surface area of the wing so that it can generate more lift when the plane is moving more slowly. So it's a pretty crucial part of the takeoff procedure. Now, in the cockpit voice recording, the pilots can be heard chatting while going through the pre-flight checklist. And while the pilots both announce the deployment of the flaps, the sound of the flap lever actually moving into position cannot be heard in the background. An examination of the wreckage confirms this finding. However, the pilots who had actually survived this crash, they were in pure disbelief. They were certain that they had deployed the flaps. And the absolute kicker in this case is that the aircraft, a Boeing 727, did have a takeoff warning system installed. So this system provides an audible warning to pilots they're going to take off with the plane in an unsafe configuration. So it literally yells at you if you try to take off without the flaps deployed. But in this case, the switch that operated the takeoff warning system had been modified to prevent nuisance activations during aircraft taxiing. So, before we wrap up, I have a confession to make. If you read the abstract, I did promise you a discussion of project failures and wrong incentives. And if I'm honest, when I wrote that down, I had a particular story in mind. Now, you can imagine my disappointment when I find out that that story isn't true. So this is the de Havilland Comet 1, the world's first commercial passenger jet. And if you ask the internet, why are aeroplane windows round? Well, you'll generally be met with a statement along the lines of, well, we tried that with the Comet and it crashed because of stress at the corners and the square windows. So let's zoom in here a little bit so you can get a better look. But it is an old photo, of course, a bit square, right? Okay, So the story gets even better because it was apparently the manager that suggested that the windows be square so as to separate air travel from the portholes of sea travel. And so because the ego-driven manager said so, and with incentives that in place that favoured not rocking the boat over prioritising safety, we got square windows and disaster. And this is all entirely believable and relatable, but all mostly untrue. The Comet did unfortunately suffer from structural fatigue issues in the fuselage. And if I've been doing my job correctly today and holding your attention in this talk, you should already have a little bit of an idea as to why. Because there's almost never any one reason for failure. And of course, this case is no different. So if you have to go, so you should already know that there's no, almost never only one reason for something. So we can sort of go back to a choice zero, so to speak, of why this happened. And if we do go back to this choice, it was essentially that they chose a specific kind of engine first, and that engine turned out to be particularly underpowered, just not powerful enough at all. And so what this did is it required the design of an ultralight fuselage, which proved susceptible to structural fatigue, which is an issue we just didn't really understand that well at the time. So now we're at the point where I make some closing remarks, and I put what I said today in a neat little package, and this is the part where I give you your list of takeaways that you can take a picture of. And before I do that, I want to acknowledge that I've probably raised more questions than answers, and that's totally fine by me. So what I want you to do is to take this list of takeaways with a grain of salt, because if there was something else that really, really resonated with you, you take that and run with it. And if you see me at the conference tomorrow, or maybe at the party tonight, I'd love to hear your take. But for now, here's what I hope you got out of this session. So first, rapid adoption of a new technology will always have problems, but it's the way that we approach these problems that matters. As a technology matures, the human element becomes even more important. So focus shifts from making the technology better to understanding the users better. More redundancy is not always the best idea. It's important to weigh the extra safety and reliability of the system itself with the cognitive load put on users to understand and interact with the system. Users is a wider definition than you think. Start thinking of yourself as a user of the system that you design and build, and see where that gets you. Lastly, the humans that interact with your systems have significant shortcomings simply because they are human. So learn to work with it, not against it. My name is Adele, and thank you so much for your time.